Important handouts. Everybody got? You didn't get, come get right now. You need them. You don't have these, get right now. This notebook look familiar to somebody? It was left outside my office. I don't know why. Got a syllabus for this class gathering contained within. So I thought possibly a member of this gang might belong to this. Key for quiz 1 will be up for this afternoon or no later than tomorrow. All right. We proceed with laying down the fundamentals for being able to get on with Bronsted-Lowry acid-base chemistry. We've talked about definitions, acids, bases, recognizing that any Bronsted-Lowry acid-base reaction is a reaction involving H+ exchange, recognizing that each and every Bronsted-Lowry acid-base reaction involves producing a different acid and a different base as products. That means different from the reactants. Learned about conjugate acids and conjugate bases and how to write formulas for such. And among other things, last Thursday in discussion class gathering, you were introduced to recognition of a very important equilibrium constant, K sub W. The W applies to water because conductivity measurements, among other measurements, have shown to establish that for any water solution at normal lab conditions, what's normal lab conditions? Roughly 25 centigrade, 1 atmosphere external pressure. For each and every water solution at these conditions, the hydronium ion concentration multiplied times the hydroxide ion concentration is 1.0 times 10 to the minus 14 to 2 significant figures. And for pure water or neutral water, neutral water is a water solution but contains no components which affect pH other than water itself. For pure water or neutral water, the hydronium ion molarity and hydroxide ion molarities are the same. That's why the water system is said to be neutral. And at NLC, 1.0 times 10 to the minus 7. For which pH and pHO are each 7.00. A particular value, use of KW is to recognize that if for any water solution at NLC I know the hydronium ion concentration, then I can immediately calculate the corresponding hydroxide ion concentration, or vice versa. Don't make the mistake of a number of students, made by a number of students when they start acid-base studies, to believe that an acidic solution does not contain any hydroxide ion. No. Acidic means that the solution has a greater, stronger acidic character than it has basic character, no more, no less. Basic means that it's more acidic than it is basic. Example, for 0.10 molar hydrochloric acid solution, given that we've recognized that in water, hydrochloric acid is ionizing by reaction with water to an extent of 100%. So here's a case where the M sub I value, the label on the bottle, is equal to the hydronium ion concentration and also the chloride ion concentration for this HCl solution. But since we're talking about acid-base properties of the solution, we don't care about chloride ion. We'll talk more about that in a moment. Because chloride ion, even though it's a negative ion, has a weaker affinity for H plus in water solution than water itself. And any such base has no ability to affect pH in water solution. Not only is it a weaker base than water, it's hugely outnumbered by water because water is the solvent. So any base weaker than water doesn't get in the pH effect game in water solution. Just like any acid weaker than water doesn't get in the pH effect game in water solution. So for this solution, hydronium ion molarity is this, which means the hydroxide ion molarity is Kw divided by the hydronium ion molarity. 1.0 times 10 to the minus 13. That's a daggone tiny value. And if you take a ratio of hydronium ion to hydroxide ion molarity for this solution, you get a ratio of 1 trillion to 1. Which shows why this solution is clearly acidic. Because the hydronium ion molarity on a comparative basis is huge next to the hydroxide ion molarity. So as we noted in our conversation, the upshot of this is that a solution, water solution, is acidic if the hydronium ion molarity is larger than hydroxide ion molarity. And if the hydronium ion molarity is larger than hydroxide ion molarity, hydronium ion molarity is going to be larger than 1.0 times 10 to the minus 7. On the other hand, if the solution is basic, the hydroxide ion molarity is larger than the hydronium ion molarity, and the hydroxide ion molarity is larger than 1.0 times 10 to the minus 7. But again, if the molarity of hydronium ion and hydroxide ion are equal for the water solution, the solution is equal in acidic and basic character. Such a solution is said to be neutral. Don't take neutral to mean it has no acidic or basic character. That's not true. It means the acidic and basic characters of the solution are equal. And under normal lab conditions, as we just mentioned in our conversation, measurements show that for pure water or neutral water, the hydronium ion molarity and hydroxide ion molarity are each 1.0 times 10 to the minus 7, from which we get the pH value of 7.00. Now then, are you all at ease in dealing with logs to the base 10? Do you understand what a logarithm is by definition? Do you understand why logarithms were established? What's the principal benefit of using logarithms from an arithmetic standpoint? Did you all use logarithms in high school? Well, then you should know what logs are. A log is an exponent, no more, no less. And when we talk about log to the base 10, we're talking about exponent on the number 10. Log to the base 8 means exponent on number 8. But arithmetic considerations done by powers of 10 is a hell of a lot simpler than any other power. Now, this is how and why pH has come to be defined as it is. Now, in truth, pH is really defined as the activity of the hydronium ion in water solution. How many of you have heard about activity? How many of you in Chemistry 2045 heard about the Van't Hoff I factor? Hand up if you did. Well, then you should have heard about activity, because that's what the I factor reflects. Activity is a term which refers to the ability of a particle, a particular particle, and a solution of that particle to behave as if it is there all by itself. If you think about it, this is what really corresponds to ideal gas behavior. Because in an ideal gas, all the component particles of the gas system are behaving independently of each other. They're behaving as if they have no volume, and they're behaving independent of any interaction on an attraction basis with other particles in the system. No interparticle attraction forces. So as we've already noted, this is why if you want a gas to have the chance to behave ideally, you heat it up and keep it at low pressure. You give it a big volume in which to live, the gas sample. Low pressure, keeping the volume large, means the volumes of the particles are negligible compared to the volume occupied by the system itself. Like if we collected all the molecules in this atmosphere we call air, in this room right now, all the molecules, 79% of them are nitrogen, or 78% of them are nitrogen, roughly, 21% roughly oxygen molecules, and a smattering of water vapor molecules, CO2 molecules, argon atoms, things like that. We could easily collect all these molecules that constitute this air atmosphere and put them in a mayonnaise jar. Now the mayonnaise jar would have to have its walls reinforced, probably by tape or something like that, because this would be a sample of gas at a particularly high pressure. But the total volume occupied by all these molecules is not much at all. Well, regarding activity now, we're talking about species in liquid solution. If you talk about activities of gases, as you'll learn in physical chemistry class, they have a fancy word for this called fugacity. That's just a term applied to activities of gases. Well, we're not dealing with gases, we're dealing with liquid solutions, particularly water solutions. And the upshot of all of this is to realize that if you want equilibrium constants to show you their true meaning, if you want pH to show you its true meaning, you have to deal with activities. Because you can't disregard interactions of particles between and among each other. But if the solution is fairly dilute, then interactions among and between the particles are often negligible. So if we keep our considerations regarding pH, the systems of hydronium ion molarity or hydroxide ion molarity, which are on the order of 1 molar or less, we're kind of stretching the truth a little bit, but activities and pHs, activities and hydronium ion concentrations will be about the same. So since we're not in position to deal with activities at this stage of the game, we'll keep this consideration on the much simpler hydronium ion molarity, hydroxide ion molarity basis. And all the stuff you see in the notes is on this basis. I'll have some more things to say to you, at least in brief, about activity when we get to chapter 19, equilibria involving salts of limited solubility in water. But I say again, for our considerations for this gathering, we are not going to be saddled with the responsibility of dealing with activities. But if you get into a good analytical chemistry class, then they're going to hold you responsible for dealing with activities. It's not all that difficult from an arithmetic standpoint, so don't be frightened by this. And chances are, as I rewrite these notes with the hope of turning these notes into a textbook, I'll have activities in there. Because you can grasp it at this stage of the game, so long as I write it up with sufficient clarity that you can understand what I'm trying to say. That's my job. If I stand here in front of you and say a bunch of stuff, none of which can be understood, I don't know what I'm doing, but teaching it ain't. Because learning can go on without teaching. But if I'm trying to be a teacher and nobody learns from what I'm doing, I don't know what the hell I'm doing, because it's not teaching. That's my job. I think you've already realized I love my job. So I'm going to try to do the best I can to help you learn. So at least I can be called a teacher. Now then, back to logs. Why were logs invented? What's the most important aspect of using logs in arithmetic, for arithmetic considerations? Did you learn this when you did business with logs? No, I guess not. Logs offer the arithmetic simplification of taking an exponential equation and by converting it to its logarithmic form, turn it into a linear equation. That's it. An equation which can be solved by addition and or subtraction. That's it. That's beautiful. Wonderful. So I say to you right now, I know doggone well that some of you, I hope not too many, but I know at least some of you are going to have trouble with this logarithmic arithmetic. Now I'm not going to take time to talk about how to use logs in here. What you need to know is in the notes. And if you need any practice on logarithmic arithmetic, if, for example, where I've told you to do questions 18, 4, 5, and 6 from chapter 18, if you have difficulty with these questions, then see a member of this instructional staff during office time, CLC time, for assistance. So I wrote, get help if necessary. There's two parts to this puzzle. If I have a hydronium ion concentration, how do I convert it to its corresponding pH? Most students don't have any trouble with that. But where they often have trouble is if I give you a pH, what's the corresponding hydronium ion concentration? And take note, if you've not yet recognized such, that pKw, do you know what the small letter p means out here in front? All by itself, the small letter p means minus log to the base 10, negative log to the base 10. That's why pH is this, because this is all the p part. Negative log to the base 10, in this case of the hydronium ion concentration, which H is shorthand abbreviation of reference to. PHO, negative log to the base 10 of hydroxide ion molarity. pKw, negative log to the base 10 of Kw. So if I express Kw as 1.0 times 10 to the minus 14, which I wrote up there, how many significant figures in that value? 2. So when I take the log of that, and take the negative of it, I'll get pKw, which must be expressed to 2 significant figures. You see this pKw value, 14.00? How many significant figures in this? How many? How many? 4. 2! I asked you if you understood logs. A log is composed of 2 parts. You know what the parts are? Characteristic and mantissa. You heard that? The characteristic are the digital components of a log which appear to the left of the decimal point, and they serve purpose of showing the position of the decimal point, or if you prefer, power of 10. Since this is a negative log, this value tells you that the antilog of this, which is Kw, is the antilog of 0.00. These are the 2 significant figures. Zeros in logs are significant. The antilog of 0.00 times 10 to the minus 14. There's your exponent part. Okay? So this has nothing to do with measurmental significance. That's a decimal point locator. So keep in mind, significant figures as shown by a log are shown only by the number of digital entries in the mantissa, the digits which appear to the right of the decimal point in a log. Now I got a feeling that a lot of you didn't know this, so you just learned something. Now a question. 18.7. Here's a reaction we've already looked at many times. We now know something about the extent of this reaction, don't we? There's its K value. What does this K value tell us? It tells us that in pure water or neutral water at NLC, that reaction goes until the hydronium ion concentration multiplied times the hydroxide ion concentration is only 1.0 times 10 to minus 14. And for neutral water or pure water, the hydronium ion and hydroxide ion molarities are equal, as the stoichiometry of this reaction equation demands that you recognize, and equal to 1.0 times 10 to minus 7, which we know by measurements such as solution conductivity. Well, what's the molarity of water in pure water? We mentioned this in passing. What is it? The molarity of water in pure water liquid. Remember what molarity is? Moles of solute per liter of solution which contains that solute. Well, in this case, our solute is water, because we're talking about pure water itself. Moles of solute, in this case moles of water, per liter of pure water. Well, tell me, if you're in a laboratory dealing with a liter of deionized water, what mass does this sample of water have?
1 kilogram.
I'm listening. 1,000 grams? You remember that the density of water at NLC is 1.0 grams per milliliter to 2 sig figs? Well, then if you have a liter of water, from a mass standpoint, you've got 1,000 grams of water. Now, what's the formula mass for water? Most students know that. Let's take it to 2 sig figs. Does 18 grams per mole ring a bell? Okay for water? 16 grams per mole for the oxygen atom. 1 gram per mole to 1 sig fig for the hydrogen atom. So the 2 sig figs, 18 grams per mole. So now I'm going to do some dimensional analysis on these data points to answer the question, the molarity of water in pure water. I want moles of water per liter of water. I got 1,000 grams per liter and a formula mass of 18 grams per mole. So I'm going to take that data point and invert it. 1 mole per 18 grams times 1,000 grams per liter. So now I got grams in the numerator, grams in the denominator. Grams cancel, right? And I wind up with a ratio of moles per liter. That's the way you do dimensional analysis. To find out if the setup which you create generates the dimensions, the units that the statement of the question or problem demand that you arrive at. Because if you write a setup that doesn't give you the units asked for, I don't care what the hell you do with the numbers, they can't mean anything. And when I divide 1,000 by 18, I get 55. If I take it to 3 sig figs, I get 55.3. I'd have to extend the formula mass beyond 18 grams. It's 18.02 grams if I go to 4 sig figs for water. Okay? Well, if I have pure water, 1 liter thereof, 55.3 moles of water, and in this sample, I wind up with only 1.0 times 10 to minus 7 moles of hydronium ion and 1.0 times 10 to minus 7 moles of hydroxide ion. You think it's a fair statement that this reaction has gone to a damn small extent? 55.3 moles of water converted to only 1.0 times 10 to minus 7 moles of this and 1.0 times 10 to minus 7 moles of that. Wonderful. Now another question. What do you know about this reaction from an exo-endo standpoint? You all know that this reaction is definitely endothermic? Now then, from what we've had to say so far, if I make the statement, and really we talked about this when we talked about writing the conjugate base formula for that fancy complex ion of magnesium. If I make the statement that we already know that hydronium ion is a lot stronger Bronsted acid than water, and hydroxide ion is a lot stronger Bronsted base than water. You accept that? Okay. Well then, another way to say the same thing is to say that given that hydronium ion is a much stronger acid than water and hydroxide ion is a much stronger base than water, the tendency for hydronium ion and hydroxide ion to react with each other and exchange H plus compares how to the tendency of water reacting as an acid with water reacting as a base to exchange H plus. How do these tendencies compare? Hydronium ion plus hydroxide ion, H plus exchange, versus water plus water, H plus exchange. Which tendency is far greater? Hydronium ion is a much better H plus giver than water. Hydroxide ion is a much better H plus stealer than water. So I repeat the consideration. Between which pair as a reacting acid and reacting base, hydronium ion plus hydroxide ion or water plus water, where do I have the much greater chance for H plus exchange to occur?
Hydronium hydroxide.
Does it make sense? Hydronium ion, hydroxide ion. If hydronium ion is a hell of a lot better H plus giver and hydroxide ion is a hell of a lot better H plus stealer, wonderful. From that you can recognize that this reaction has got to be endothermic as written. Because the tendency of this thing to give H plus to this thing is far greater than the tendency of this thing to give H plus to this thing. Well then, what happens therefore to this reaction? If I take a sample of pure water and heat it up, let's apply extreme pressure to it so that I can prevent vaporization, or at least boiling, and really heat this water, make it super hot water liquid. What happens to this reaction? What happens to the value for Kw? For very, very hot water compared to NLCKW of 1.0 times 10 to minus 14. What happens to Kw if I take my pure water and keep it under pressure and heat the hell out of it? Will I have Kw stay the same, get larger, or get smaller? Three possibilities exist, only one of which is correct. Get larger, because this is an endo reaction, right? And what do you have to put into an endo reaction to make it go? So at the instant at which I add heat to this, the equilibrium is murdered, and to get me back to equilibrium, this is the reaction which takes place to do so. Okay? So I ask the question. If I measure pH and pHO for very, very hot, high pressurized water, what kind of values will I get comparatively? In other words, how will pH and pHO compare? And how will the pH value and pHO value compare to 7.00, because that's pH and pHO at NLC? That's the question.
pH is going to go, it's going to be less than pHO is going to be more.
How will the pH value for the super hot water compare to 7.00? The pH value.
It's going to be lower than 7.00.
Good deal lower.
More acidic.
How will the pHO value compare to 7.00? I'm listening. Do you see this reaction? Because in pure water, the only components I have is water, water, and these things, right? And we recognized, if I heat the hell out of pure water and keep it under pressure, this thing is not only going to go left to right as written, it's going to go to a large extent left to right as written. And the stoichiometry of this reaction demands that you realize that in this system, the only source of each of these is reactant water. So if this thing goes to a much larger extent, because of the conditions which I've established, a much higher temperature under pressure, then this molarity does what? Molarity of this And the molarity of this? Increases. The system becomes much more acidic and much more basic. How do you like them apples? That's why hot, high-pressure steam is corrosive. How about that? It is corrosive because it's quite acidic and quite basic. The pH is a good deal less than 7.00, and pHO is a good deal what compared to 7.00? Greater or less?
Greater.
No! Or yes. pHO is negative log to the base 10 of the hydroxide ion concentration. Okay, so far? pHO. I'm going to give you two pHOs. 0.0 and 1.0. You understand these numbers? 0.0 and 1.0. Which of these pHOs corresponds to the solution which is more basic? 0.0 or 1.0? Which one is it? 0.0, isn't it? Yeah. Now, would you like to answer this question again? Going to heat the hell out of this system. The pH value becomes a number which is a lot smaller than 7.00. Okay so far? Because the system has gotten much more acidic. Okay? Now pHO. The hydroxide ion concentration is also increased to the same extent that the hydronium ion concentration is increased, right? So what happens to pHO relative to 7.00? It's gotten much lower, just like pH. They wind up being the same value. They have to be the same value. Remember, this is pH and pHO. I didn't ask you about pH for both cases. Now, the consideration we just made was really asking you to recognize what you can understand about this system after you realize it's endothermic. Now, we're not going to deal with acid-base systems in the chemistry we're going to consider in Chapter 18 as a consequence of heating the solution or cooling the solution. We'll keep everything at NLC. So what you're going to realize for the solutions we deal with is, if to a water solution, or water itself, you add an external source of hydronium ion, like adding HCl to water to make hydrochloric acid solution, okay? That guarantees an increase in the hydronium ion concentration, and at the same time guarantees a decrease in the hydroxide ion concentration to the same extent that you increased the hydronium ion concentration. That's not the same as this system. If you're puzzled by this, think about it. It'll come clear. And if you're puzzled by this and think about it and it doesn't come clear, ask us. But this is discussed in the notes. And so you should have read that before you just heard me sermonize on it. I hope you have. Now let's begin to get at the real heart and soul, nuts and bolts of Bronsted Lowry acid-base chemistry, as we shall deal with such in Chapter 18. This is going to obligate us to learn some language. The language which we're going to learn relates directly to the information you see in these handouts. Directive. I want you to have these handouts with you for each and every class gathering and have them in a readily available position. Because we're going to refer to the information on these handouts, especially this thing, regularly. So in talking about such, I don't have to write it on the board. You'll have it. If you lose this, I'll give you another one for $2. You lose that one, $5. I got to get beer money somehow. Okay? This is a smaller piece of paper, so if you lose this, $1.50. Statement. On each and every in-class quiz and exam, from now on, you'll get this information sheet. Now, last I heard, the 2045 people were requiring you in preparation for an exam to memorize equations. Did you do that? Didn't have to do that? Good. That's stupid. What you want to do is be able to use this stuff. So I've given you all this stuff on this information sheet. You take a look at it. For now, all we're really interested in is the acid-base table and the information that's immediately attached to the acid-base table. That's what you see underneath the acid-base table. Because we are going to be using this stuff as we go through Chapter 18. Strong acid. It's all in the notes. Look at the acid-base table. In our acid-base table, we have listed the formulas for 1, 2, 3, 4, 5 strong acids. Count them. Hydronium ion and the 4 acids whose formulas appear above hydronium ion in the acid column. My definition of a strong acid in water solution is hydronium ion, because hydronium ion is the strongest acid you can ever have at high concentration in water solution. And any acid stronger than hydronium ion. Strong base in water solution. What do you think the definition is? Strong base in water solution. What do you believe the definition is? The information on this acid-base table will answer the question if you can relate what I just said to you about hydronium ion and the acid stronger than hydronium ion to get a handle on strong bases in water solution. Hydroxide ion and the base is stronger than hydroxide ion. That's it. So in this table, we only have 3 strong bases. Hydroxide ion, sulfide ion, and oxide ion. That's it. Oxide ion is the strongest base listed in this table. That shouldn't be too surprising. It's a monatomic species, which is derived from a rather small atom, the oxygen atom, pretty small atom. And it's got a substantial degree of charge. So its charge density, negative charge density, will be quite significant. Oxide ion, a damn strong Bronsted base. Okay? Weak acid. Any acid listed underneath hydronium ion in this acid column. Now there are 2 categories of weak acids. One category of weak acid we care about because they can show their acidity to us in water solution. These are the acids, including water, which are in this table underneath hydronium ion in the acid column, but above water. Water and those above water. Those are the weak acids whose acidities can be observed in water solution. Now then, you'll see a couple of hydrogen-containing material, because clearly if you're going to be an H+ giver, you've got to have hydrogen in your composition. You see a couple acids which are weaker than water. For our table, that means HS- and hydroxide ion, the conjugate acids of the very strong bases sulfide ion and oxide ion. Those acids are so weak that they will not behave as H+ givers in water solution unless we trick them by some fancy chemistry. But if what you do is to dissolve in water a source of HS- or a source of HO-, those things will react as Bronsted bases. They will not react as Bronsted acids. There's ways to get them to lose H+, but not by reaction with water. We'll talk about that later, not now. So with what I've said to you, in this acid-base table, in the base column, which bases are those that are going to be categorized as weak bases and have an ability to affect pH measurably in water solution? They will be the bases in the base column, water included, that take you all the way down to what? All the way down to what? Hydroxide ion. all the bases in the base column. Water and all those immediately underneath till you get all the way to hydroxide ion. All those bases can behave as H plus grabbers in water solution. But those above water in the base column, even though, interestingly enough, perchlorate ion, hydrogen sulfate ion, chloride ion, and nitrate ion, those things have negative charges. They're anions. But in water solution, even though these have negative charges, they do not attract H plus as strongly as water itself. So chloride ion, nitrate ion, and similar species, in water solution, they show no ability to compete for H plus, practically speaking. Because water's a stronger base than they are, and water outnumbers them grossly. Because water's the solvent. Okay? So that gives us a handle on strong and weak bases. So, back to definitions, which follows from what we've just said. Strong acid, hydronium ion, every acid, any acid stronger than hydronium ion. Strong base, hydroxide ion, and any base stronger than hydroxide ion. Weak acid, water, and every acid stronger than water but weaker than hydronium ion. Weak base, water, and every base stronger than water but weaker than hydroxide ion. Now you know how to immediately recognize strong acids, weak acids, strong bases, weak bases from the information on this table. Now then, a particularly important use of this information is to be able to play the principal system inventory game, PSI. Because as we have reminded you, if you're going to do correct chemistry which you can understand on a chemical system, at the minimum, you have to start by knowing what the system contains mainly, the main system ingredients. And to do that, you write a PSI, Principal System Inventory. You remember doing this in 2045 lab? I had you do an assignment 4 to try to get you, at least to some extent, in the know about this issue. Textbooks are notoriously horrible about this for general chemistry. Horrible. That's why they have so many equations for reactions in water solution written incorrectly on their very expensive pages. And that's why those books don't get in this classroom. PSI. What's in the system? Mainly. Main system ingredients. Now, take a look at this sheet. Second sheet you picked up today. Writing a principal system inventory. PSI, chemical formula list of principal system components. Quantitative PSI. So now you must recognize there are two aspects to inventory. I got a feeling your horse sense would tell you this. If, for example, you have a job as a store clerk at one of the local public supermarkets, and the boss tells you to write an inventory. The boss gives you a big steno pad and pencils and says, please give me a complete inventory. What will you do if you're going to comply with this directive? A complete store inventory. What would you do? What would you do? Or am I to gather that nobody wants to get a job at Publix? Is that right? What would you do? You go around a store and you write down the name of each and every stuff you got in the store. That's a lot of stuff. Grade A whole milk. Publix, Ma and Pa, Gustafson, who knows whatever. We got a whole bunch of different kinds of milk. Okay? Now, what if the boss says, in making this inventory at Publix, I also want you to decide whether or not at this moment we need to order any more of this stuff. So what's the second part of an inventory? The first part is what you got. What's the second part? How much? Those are the two parts. Now initially we will be concerned with the what you got part. But when we get into equilibrium analysis of acid-base solution systems, then we got to pay attention to the how much part. And if we're dealing with how much in chemistry, what's the how much quantity we refer to? What is it? Moles. And keep in mind that moles and molar concentrations are not the same. If I tell you a solution on the side shelf bears the label 1 molar hydrochloric acid solution, have I told you how many moles of hydronium ion and how many moles of chloride ion you have in this solution? No. What if you've only got a milliliter of this solution? Hey, you don't have many moles then. But if I got a big 50-liter drum of this stuff, then you got a hell of a lot of moles. So don't get moles and molar concentrations mixed up. Because when you're going to do a quantitative inventory, QPSI, you got to talk about moles, which means you will likely have to take concentration values, moles per liter, and multiply by what to get moles? By what?
Volume.
Solution volume, right? Then the liters go away. Dimensional analysis. Now then, this sheet sums up all the PSI considerations for which you are responsible. The PSI considerations that you need to know. And they all follow from what we have talked about so far. If I make a water solution of an acid, like hydrochloric acid, where that acid is stronger than hydronium ion, the acid will react with water and convert the hydronium ion and the conjugate base of the acid, which is chloride ion for HCl. To what extent? Practically speaking, how much? 100%. So how's this system going to inventory? Is it going to be HClAQ? Like the stupid damn textbooks, right? It's pretty good when you write a formula for something that ain't there. What good is this? Hydronium ion, chloride ion, and of course the solvent water. On the other hand, if I make a water solution of a weak acid, let's consider making a water solution of the best known weak acid of all time. Shorthand abbreviation formula is HAC, acetic acid. Why is that the best known acid of all time? Way back in pre-biblical days, people were interested in preparing potable fluids. You know what potable fluids are? Booze, beer, wine, stuff that's got ethanol in it. You know, have a party, oh boy. And what is the most common way by which ethanol-containing fluids are prepared? It's still done in many places in the hills and valleys of Kentucky and Tennessee and Georgia. where they make stuff called moonshine. You ever drink moonshine? Corn whiskey? I like it. Good, straight, clean, potent taste. Ha ha! I like it. I'm not kidding, I like it. The process by which they make the moonshine is called what? Fermentation. You've heard that, haven't you? Well, they knew about fermentation way back in pre-biblical days. Unfortunately, with fermenting some natural materials, along with making alcohol, ethanol, ethyl alcohol, which is the potable alcohol, they also made acetic acid. They didn't want to make the acetic acid, but they couldn't avoid it. But that's how acetic acid got to be known as the best known acid of all time, because chemistry's been done with acetic acid for thousands of years. But now let's get to the nitty-gritty of this, which I remind you we already discussed to some extent. In making acetic acid solution, since acetic acid by definition is a weak or strong acid, look at the table. Weak acid, isn't it? It's underneath hydronium ion but above water. If I make a water solution of acetic acid, will acetic acid react with water? And in this case create hydronium ion and acetate ion, the conjugate base of acetic acid. Will acetic acid react with water to a large or small extent, keeping in mind that number one, a material is found to be an acid if it can react with water to produce what? Hydronium ion. And hydronium ion is an acid which compares how strength-wise to acetic acid? Hydronium ion is stronger, isn't it? So between which reacting pair, acetic acid and water, or hydronium ion and acetate ion, is the tendency for H plus exchange greater? We talked about that here. Now let's apply it to this case. Between this and this as reacting acid and base, or this and this as reacting acid and base, where's the greater tendency for H plus exchange to exist? Between the stronger acid and the stronger base, isn't it? If I made a system where I started with 1 molar this and 1 molar this and 1 molar this, would that system stay as such? What would happen in that system? Initially, 1 molar this, 1 molar this, 1 molar this, water's dissolved. What would happen? What would happen? 1 molar this, water's dissolved. 1 molar this, 1 molar this, 1 molar this. If I make that system, will more acetic acid react with water and make these molarities go up above 1? Or would these react and make these molarities get lower than 1 while I made more of this stuff? What would happen? What would happen? Is the tendency between these for H plus exchange greater than the tendency between these? So if these are all present at the same concentrations, and these are better H plus exchangers, here's where the net H plus exchange is going to occur. So if I made this system I just described, 1 molar this, 1 molar this, 1 molar this, which corresponds to a set of conditions I asked you to learn about in 2045L last term in assignment 7. Do you remember what those conditions are? You think I was laying foundation for this course in 2045 lab? You're damn right. Because this stuff is tough, but this stuff is important. The conditions to which I refer are known as standard state. Remember that? 45 lab assignment 7 discussion? The damn administration of this university would ever realize that having you folks working there on a partnership basis is an atrocity? We'd get someplace with that course. But no, they're more interested in accommodating enrollment requests and let education value go right down the damn drain. I hope you hear me, Machen, and all your buddies. I mean it. This stuff is on the internet. I've had it with this junk. This place seems to be far more interested in seeing how many hind ends after 4 years they can stamp UF certified. Well, what does that certification mean? If you haven't learned anything, what the hell is it good for? To me, it's not good for anything. It's a lie. And I don't want that. I want you to go away from this course really knowing some chemistry. And that's what we're going to do. I think you know that by now. Upshot. When I make a water solution of a weak acid, given that this product acid is stronger than this reacting acid, the reaction extent for most such solutions will be small. Which means that for a water solution of a weak acid, what will the PSI be? Hydronium ion and the conjugate base, or the weak acid itself? Water, of course, included. Weak acid itself. Bingo. And that's what's on this PSI sheet. So now you recognize. If you use the acid-base table as a crutch, and I want you to. I mean, I see this thing in my sleep. I love it. Makes me happy. If you do this as many times as I've done it, you'll see it in your sleep. But for now, I don't expect you to memorize any of this stuff. I expect you to see it and use it. PSI, water solution strong acid, hydronium ion conjugate base in water. PSI, water solution weak acid, the acid itself in water. PSI, strong base, hydroxide ion, water itself, and conjugate acid of the base, and probably counter ion, because most strong bases are salts, like sodium hydroxide. Okay, so you got to put the sodium ion in there. Now, do we care about the sodium ion's presence from an acid-base standpoint? You'll find out in a moment. Hell no, we don't care. That's why you don't see sodium ion, for example, in our acid-base table. And water solution of a weak base, the weak base itself in water. That's it. Okay? Now, what about writing an inventory, a correct formula for any pure substance? That's nothing to it. It's the pure substance. If I deal with hydrogen chloride gas, it's hydrogen chloride gas, period. It's just a cylinder of that stuff, nothing else in it. No reaction has yet occurred. It's not in solution. Now, before we pass by this, let's reflect in brief on one particular type of weak acid. First, look at the acid-base table. On the acid-base table, or I shouldn't say first, but again, look at the acid-base table. You will see in the acid column the formulas for some hydrated metal ions. Do you see these? The strongest acid among the hydrated metal ions listed in our acid column is hydrated iron plus 3. Do you see that? The next one is hydrated aluminum plus 3. Okay? And then you'll see a few others. Statement number 1. All hydrated metal ions are weak acids in water solution. None of them are strong acids. How do these hydrated metal ions form? And what kind of chemistry do they exhibit? Well, they're acids. They must be behaving as acids. So let's imagine for the moment we put you in 46 laboratory, where many of you really are during the week. And you see a bottle that bears this label on the side shelf. Colorless solution. Okay? Now you're here with this crazy guy trying to get you to learn acid-base chemistry. And he screamed up and down that in order to be able to do this for any system, you need to know the PSI, right? So what's the PSI for this system? Statement number 2. 1 molar aluminum nitrate solution. I'd expect you to all realize at a glance that aluminum nitrate by itself is what kind of a compound categorically? Ionic or molecular? Ionic. Aluminum ions and nitrate ions are the component ions. But if you take some of this solution, and you are going to do this in assignment 4, it might not be aluminum nitrate, but so what? It'll be aluminum ion containing solution. And you observe the pH of this solution, you'll find out that it's on the order of 3.0. That's a fairly acidic solution. Neutral water, 7.0 pH. This is 4 pH units away from that. So this solution is 10 to the 4th greater in hydronium ion concentration than neutral water. 10 to the 4th. That's 10,000. This solution is 10,000 times more acidic than neutral water. 10,000 times. Why? What's going on? Hydronium ions can't come from this stuff. Nitrate ions, these are weak bases, right? So weak they don't even behave as bases in water solution. And here's aluminum ion. This is the label you see on the bottle. And that label tells you how the solution was prepared. It does not tell you what's in the solution. Your knowledge of chemistry will tell you what's in the solution. And that's what we're doing right now. We're programming you to expand your knowledge of chemistry so you can correctly inventory a solution such as this. So what do you have to learn about? You have to learn about hydrated metal ions and how they form. Well, they form from the chemistry of the metal ion itself in the presence of water molecules. Now, I know you can all write the formula for aluminum ion. Charge? Indeed, aluminum ion derived from aluminum metal in family number 3A. We've got 3 valence electrons. The only chemistry which aluminum atoms ever show, they've never been found to show any other chemistry, is when they react, they lose 3 electrons per atom and become Al with a charge of +3. Okay? But I'm introducing this aluminum ion into a water solution. That's how I made this stuff, right? I dissolved aluminum nitrate in water being my solvent until for each liter of solution that I prepared, 1 mole of this stuff was dissolved. Okay? So when I put this in water solution, like all ionic compounds, what does this ionic compound first do? Dissociates, right? Ionic compounds, as they dissolve in water, dissociate. And what do they dissociate into? They're component ions. Aluminum ions and nitrate ions. So now you're an aluminum ion, set free to swim about in this solution, rich in water molecules. Here you are. And here's the water molecule. The water molecule observes you, and you, the aluminum ion, observe the water molecule. Is that the end of this interaction? You just look at each other and swim by merrily and keep going as if you're individual species? Or is it the case that this thing, because it's small and it's got a substantial plus charge, doesn't it? This thing has a high positive charge density. And something with a high positive charge density effectively attracts negative charge density attributable to non-bonding electron pairs on the central oxygen atom of the water molecule. Ain't that right, Coulomb? So what happens? What happens is these water molecules swim over to this aluminum ion. In fact, per each aluminum ion, as the formula in the table tells you, per each aluminum ion, how many water molecules swim over to and glue on to an aluminum ion? 6 of them. And they make a species which has this geometry. What is this geometry? I showed you this geometry when we talked about this complex ion of magnesium ion. Now we're doing it for aluminum ion. It's octahedral. At the 6 corners of this octahedron, you have water molecules. And in the center of this octahedron, you have the aluminum ion. Why don't more water molecules glue onto the aluminum ion than 6? I'm asking. Why does the glue-on factor, water molecules to aluminum ion, stop at 6?
Too small.
Well, I'll ask this question. How many BBs can you glue to a basketball?
A lot.
How many ping pong balls can you glue to a basketball? A hell of a lot? How many basketballs can you glue to a ping pong ball? 2. Nothing fancy about that. So the thing is, because water molecules have size, just like the aluminum ion, but the aluminum ion is a pretty small sphere, the most water molecules you can stack around the aluminum ion and have them make contact so you can get coordinate covalent bonds involving non-bonding electron pair on the water molecule landing in an empty valence orbital of the aluminum ion to make a formal coordinate covalent bond. This happens until you got 6 of these water molecules wrapped around this in an octahedral fashion, and then there's no more space. Now then, tell me, here we have attraction. The non-bonding electron pairs are pulled closely, strongly, to the aluminum ion because of its high positive charge density. But what do we have, coulombically speaking, between the metal ion with its high positive charge density and the hydrogen atom ends of a water molecule that's stuck onto aluminum ion? Do we have here an attraction force or a repulsion force? Repulsion force, because these are the squiggle plus parts of a water molecule, right? And the stronger this bond, the greater the positive charge density, the greater the tendency for an oxygen-hydrogen bond to break like that. And that's what this repulsion winds up doing. And that's why this solution is acidic, because this hydrated aluminum ion kicks H plus away from one of its water molecules that's bonded to it, and the H plus swims off into solution and makes a bond with what species in the solution? If you're H plus and you jump into a water solution, I didn't tell you what's in the solution yet. If you're H plus and you dive into a water solution, what will you stick to for sure? What's the correct answer all the time?
Water.
Water solution. I didn't tell you what's in the solution. You're H plus, you dive into this solution. What are you going to stick to?
Water.
I want the answer that's right all the time. The strongest base that's in the solution at high concentration. That's the stuff you're going to stick to. If the solution you jump into is 1 molar sodium hydroxide solution, you're going to stick to hydroxide ion. But if you jump into pure water, then you're going to stick to water. And in so doing, what are you going to make?
H3O plus.
Hydronium ion, aren't you? So, we've just talked about all the chemistry, which accounts for and explains why metal ions in water solution have the ability to make pH go down. We're making this solution. What happens first? Dissociation. But these things, because of their high positive charge density, they don't sit there as bare species in water solution. But interact with water molecules, because in straight water, which is used as my solvent, the water is the strongest base present in high concentration. And when these things glue onto this, they make this. And And that's accounts, just what we did was just to account for the development of hydrated aluminum ion, and the same chemistry applies to developing any of the hydrated metal ions that you see in the acid column of the acid-base table. One more question. In this solution containing hydrated aluminum ion, where hydrated aluminum ion reacts with water to make hydronium ion and the conjugate base of hydrated aluminum ion, will that reaction proceed to a large extent or a small extent? Small extent, because hydrated aluminum ion is a weak acid. Bingo, we'll pick it up from this point tomorrow.